Imagine you could pause the world, open the environment like a blueprint, and compute, without trial and error, exactly how good every state is and what the best move should be from there. No exploration, no guesswork, just pure planning. That's the promise of dynamic programming in reinforcement learning. Most RL tutorials start with learning from experience, but DP is the clean origin story. It shows the idealized version of value updates and policy improvement when you actually know the rules of the environment. Once you see DP clearly, you'll start recognizing its fingerprints everywhere. TD learning, Q learning, even modern deep RL methods. In this episode, we're going to do three things. We'll evaluate a policy to get a value map. We'll improve that policy using one-step look ahead. And then we'll fuse those ideas into the two classic control engines, policy iteration and value iteration. By the end, you'll understand what it means for an agent to solve an environment as a fixed point of Bellman backups. So if you've ever looked at the Bellman equation and thought, okay, but how does this become an actual algorithm? This is the part of the series where it finally becomes real. Let's jump in. Dynamic programming is planning with a model. Instead of learning solely from sampled experience, we assume we know how the environment works, what happens when we take actions, and what rewards we get. With that model, we can compute values by repeatedly applying the same logic until everything is consistent. Dynamic programming is not how most real-world RL systems learn directly because we rarely have perfect environment dynamics. But DP is incredibly important because it reveals the clean version of the update rules that later methods approximate with sampling, like Monte Carlo and temporal difference learning. Policy evaluation asks a very specific question. If we commit to a particular policy, meaning a fixed way of choosing actions, what is the long-term value of each state? We want a number for every state that tells us how much reward we can expect if we start there and follow the policy. Those numbers matter because they turn behavior into a measurable object. Once you have a value function, you can explain what the policy is actually doing, which states are safe, which states are risky, and where the policy tends to drift over time. At the core of policy evaluation is a recursive truth. The value of a state depends on the value of the states that come next. If I'm in state S, the return I'll get is the reward I receive now, plus the discounted return I'll get later from the next state. The policy matters because it shapes which actions we take. The environment matters because it shapes where those actions take us. Policy evaluation is just the disciplined act of averaging over both, the randomness of our action choices and the randomness of the environment transitions. If we write it mathematically, the Bellman expectation equation for a policy pie says that the value of a state equals the expected reward plus the discounted value of the next state, where the expectation is taken over actions from PI and transitions from the environment. You don't need to memorize the symbols. The meaning is the key. Value is an average of reward now plus value later. That sentence is what dynamic programming turns into an algorithm. In principle, we could solve policy evaluation by treating the Bellman equations as a system of linear equations and solving them exactly. But in many practical settings, that's too expensive. So dynamic programming does something simpler and surprisingly effective. It iterates. Iterative policy evaluation starts with an initial guess for the value function, often just zeros everywhere, and then repeatedly updates each state's value using the Bellman expectation equation. Each sweep uses the model to push value information through the state space. What's happening visually is important. Terminal rewards or high reward regions influence nearby states first, then that influence spreads outward over successive updates. It's like you're filling the environment with value pressure until it reaches equilibrium. We stop iterating when the value function stops changing by more than a tiny threshold. With a discount factor gamma less than 1, These Bellman updates form a contraction, meaning repeated updates must converge to a single fixed value function for the policy. The discount factor gamma is also a storytelling tool. Low gamma makes the values focus on immediate rewards. High gamma makes them care about distant outcomes. When you change gamma, you're changing how far into the future the policy evaluation looks. There are two common ways to implement the sweeps. In synchronous updates, you compute a new table from the old one and replace everything at once. In-place updates, you overwrite values as you go, so later updates in the sweep can use fresher information. In-place updates often converge faster in practice because information propagates more quickly during each sweep. The takeaway isn't the implementation detail, it's the idea that policy evaluation is a repeated consistency process. Keep updating until the values agree with the expected future implied by the policy and the model. Let's imagine a simple grid world where the policy is random. From each state, the agent picks up, down, left, or right with equal probability. Even though the policy isn't smart, policy evaluation will still produce a meaningful value map that describes what random wandering leads to. States closer to a positive terminal outcome will typically have higher value because even random movement has a decent chance of stumbling into the goal. States near penalties or traps will have lower value because random movement tends to drift into bad outcomes. The value function becomes a clear summary of the policy's consequences. Policy evaluation is not about finding the best policy. It's about accurately measuring a given policy. If your policy is bad, evaluation doesn't fix it. It simply tells you in detail exactly how bad it is and where it fails. This is why policy evaluation is such a perfect first step in dynamic programming. It gives us the information we need to improve. Once we can compute VPI, we can ask the natural next question. If these are the values, what actions should we take instead? So the core of policy evaluation is this. We use the environment model and the Bellman expectation equation to repeatedly update state values until they stabilize. That stabilized function VPI is the long-term scorecard for the policy, state by state. In the next subpart, we'll take those values and perform policy improvement, turning the scorecard into smarter behavior. And once we combine evaluation and improvement in a loop, we get the full dynamic programming control algorithms, policy iteration, and value iteration. Now that we can evaluate a policy and turn it into a value map, we can finally ask the fun question: how do we make the policy better? Policy improvement is the step where we take what the value function tells us about the future and use it to change behavior, state by state. Policy evaluation is measurement. Policy improvement is decision-making. If evaluation is the report card, improvement is the training plan. It uses the report card to change what the agent actually does. In dynamic programming, this is possible because we assume we know the model, so we can look ahead and compare actions without needing to try them in the real environment. Policy improvement doesn't require a mysterious trick. It's a structured version of a very human idea. If one choice reliably leads to better outcomes than another, start choosing it more often. In RL terms, better outcomes means higher expected return, which is exactly what value functions summarize. To improve a policy, we need to compare actions. State values alone tell us how good it is to be somewhere, but improvement requires knowing how good it is to do something. That's why we introduce the action-value perspective. For each state, we score each action by looking one step ahead using the model and the value function we already computed. In plain language, the action score is, if I take this action, what reward do I get right now? Where do I land? And how valuable is that next state? Because we already have VPI of S prime from evaluation, we can turn the next state into a number and compare actions immediately. The key move in policy improvement is greedy choice with respect to the value estimates. For each state, we look at all possible actions and pick the one with the highest expected reward, now plus discounted value later. That creates a new policy that is at least as good as the one we started with. This at least as good guarantee is not just motivational, it's the reason dynamic programming control works. If your new policy always chooses an action that looks better according to the evaluated value function, then your expected return from that state can't decrease. Apply that logic across the whole state space, and the policy improves systematically. A pure greedy improvement often produces a deterministic policy, one best action per state. In many DP textbook settings, that's exactly what we want: clean, decisive, and easy to visualize. You can literally watch the policy become a set of arrows that point toward good outcomes. But sometimes you don't want to go fully deterministic immediately. If two actions are nearly tied, or if you're thinking ahead to later methods where values might be approximate, you can do a soft improvement. Increase the probability of better actions without forcing the others to zero. It's a smoother upgrade rather than a hard switch. Let's reuse the grid world idea. Suppose we evaluated a random policy and got a value heat map. Policy improvement takes that heat map and turns it into direction. In each cell, choose actions that move you toward higher value neighbors. You'll see arrows align along paths to the goal and away from penalties. After even one improvement step, the policy often looks dramatically more intentional. Before, movement was scattered. After, you start seeing structure, routes, avoidance behavior, and consistent directionality. This is one of the most satisfying moments in dynamic programming because it's planning you can literally see. There's an important catch. As soon as you change the policy, the old value function is no longer exactly correct for the new policy. So improvement naturally demands another evaluation step. That's not a weakness. It's the rhythm of control. Evaluate the current behavior, improve it, then re-evaluate the upgraded behavior. This pairing is what becomes policy iteration when you keep evaluation and improvement as separate phases. And if you blend them more aggressively, you get value iteration. So policy improvement isn't just a standalone trick, it's half of the engine that drives dynamic programming toward optimal behavior. Policy improvement is the moment the value function stops being just a description and becomes a lever. We take what we know about long-term outcomes and update the policy to choose better actions. Combined with policy evaluation, this creates a feedback loop that pushes behavior toward optimality. Next, we'll connect everything into the complete dynamic programming control methods, policy iteration and value iteration, and you'll see exactly how these loops converge to optimal values and an optimal policy. We've done the two building blocks. Policy evaluation gives us a value map for a fixed policy, and policy improvement uses that value map to update the policy. Now we connect them into complete control algorithms, methods that don't just analyze behavior, but repeatedly upgrade it until it becomes optimal. At a high level, dynamic programming control is a feedback loop. You start with any policy, evaluate it to understand what it's worth, improve it to make better choices, and repeat. Each cycle reduces wasted moves and increases expected return until there's nothing left to improve. What optimal means here is very specific. You reach a point where the policy is greedy with respect to its own value function. When you evaluate the policy, the values you get don't suggest any better actions anywhere. So the policy becomes stable, and the loop naturally stops changing. Policy iteration is the most direct version of this idea. You keep evaluation and improvement as separate phases. First, you evaluate the current policy until the values are accurate, then you improve the policy greedily using those values, and then you go back and evaluate again. The reason policy iteration feels powerful is that its evaluation step is strong. By letting the values settle, the improvement step is acting on solid information. So each improvement often creates a noticeable jump in policy quality across many states at once. When policy iteration converges, it usually converges cleanly. The improvement step stops changing the policy. Once the greedy choice matches what the policy already does in every state, you've hit a fixed point, an optimal policy for the model you're solving. There's also a practical variant you'll see a lot. Instead of evaluating all the way to convergence every time, you evaluate for just a few sweeps, then improve again. This modified policy iteration keeps the loop moving and often saves computation while still trending toward optimal behavior. Value iteration takes a different approach. It collapses evaluation and improvement into a single update rule. Instead of saying evaluate this policy, it directly updates the value function as if the agent will choose the best action from each state. This is the key conceptual switch. Policy evaluation uses an average over actions according to a policy, but value iteration replaces that average with a max. It's essentially asking, if I acted optimally from here, what value would this state have? And then iterating until that answer stabilizes. In value iteration, the policy doesn't need to be explicitly updated every loop. You refine the value function first, and once the values are close to optimal, you extract a policy by choosing the action that looks best under those values. The policy is like a shadow cast by the value function. Value iteration often takes more iterations than policy iteration, but each iteration is usually lightweight. You're doing small, consistent pushes toward optimal values, and you can watch the value landscape become stable as the greedy action choices stop changing. Both algorithms aim for the same destination, the optimal value function and an optimal policy. Policy iteration tends to take fewer, heavier steps because it evaluates more thoroughly before improving. Value iteration tends to take more, lighter steps because it improves continuously inside the value update. A useful way to remember the difference is that policy iteration treats the policy as the main object and repeatedly upgrades it, while value iteration treats the value function as the main object and lets the policy fall out at the end. Same math family, different emphasis. In a small grid world, policy iteration often reaches an optimal or near-optimal policy in just a handful of loops because each improvement step can reorganize decisions everywhere. Value iteration may take longer, but it's incredibly visual. You see the values settle, and the implied greedy policy gradually becomes consistent. In both cases, the stopping signal is stability. With policy iteration, the policy stops changing. With value iteration, the value updates become tiny everywhere, and the greedy action choices stop flipping back and forth. When nothing meaningful changes, you're done. This subsection is where dynamic programming stops being a special case and starts feeling like the template for RL. The idea of Bellman backups, greedy selection, and fixed points shows up again when we don't have a model, except then we estimate the same targets from samples. DP gives you the clean version so you can recognize the structure later. So policy iteration is the classic evaluate then improve loop, and value iteration is the streamlined optimality update that bakes improvement directly into the value function. Together, they complete the dynamic programming foundations, planning with a model until values and policy settle into an optimal fixed point. That's it for Part 7, Dynamic Programming Foundations. We started by evaluating a policy, turning behavior into a value map. Then we used those values to improve decisions, and finally we connected everything into the full control algorithms: policy iteration and value iteration. If you can explain that loop in your own words, you've basically unlocked the blueprint behind a huge chunk of reinforcement learning. Dynamic programming is also a reality check. It shows what RL looks like when you have a perfect model of the world. That's not always realistic, but it's incredibly useful, because later, when we go model-free, you'll recognize the same shapes hiding underneath. Bellman backups, value estimates, and greedy improvements, just approximated and learned from experience. If you want to solidify this, try a tiny grid world on your own. Compute values for a simple policy, improve it once, and watch how quickly structure emerges. The moment you see random arrows turn into purposeful paths, DP stops being abstract and starts feeling like planning you can literally visualize. In the next part, we'll start loosening the perfect model assumption. We'll keep the same core idea, updating value estimates and improving behavior, but we'll learn from sampled experience instead of complete transition probabilities. That's where dynamic programming turns into the stepping stone for Monte Carlo methods and temporal difference learning. If this episode helped, drop a comment with the environment you'd like to see next. Grid world, gambler's problem, cliff walking, something else. And I'll use it as the running example as we move into learning from experience. See you in the next video.